Okay, thank you. I start by thanking the organizers for this meeting and for allowing me to deliver this talk. So I will be talking about the stability conditions for the scalar field or the Horndeski scalar field gravity. So the scope of this talk will be why we need to seek beyond general relativity. So to introduce the Horndeski gravity model and to talk about another problem that we have, which is the energy in gravity, and to present our results and to later discuss some of the conclusions that we reached. Okay? So why not general relativity? So we all are aware of the successes of general relativity, namely at solar system level, the explanation of the perihelion precession of Mercury's orbit, or even the impressive agreement with the recent the stringent bounds on the speed of gravitational waves. Nevertheless, there are some issues, there are some conundrums in general relativity, namely the existence of singularities, the large-scale problem of dark matter and dark energy, somehow it lacks a fully consistent quantum version, and, for instance, the cosmological constant problem. Okay, so we do really have some treatments for these problems. Some of them rely on goodwill, which is like looking into the so-called CDM paradigm, which is looking into dark energy as a cosmological constant and dark energy being cold. So we can postpone the problem of singularities to once we reach a fully consistent quantum version of gravity. So we know that it matches the most of the data that we know, but so did Newton's law back then. And well, the general relativity is simple and beautiful. Why we need to spoil that? So leave it that way. But we need to be very surgical in what concerns to addressing these problems. We need to seek beyond general relativity. And how can we change gravity? We can either change the pure gravity sector. Let's look into the Einstein field equations. We change it, adding more curvature or less, or how this can occur. And one example is the well-known F(r) theories. Or we can modify the energy content of the universe, or the Einstein field equations, by, for instance, introducing dark matter and dark energy fields. But we cannot push this even further by introducing non-minimal couplings or changing the way that the gravity and the matter, the energy momentum, feel each other. Okay? So these are really some wedding proposals by trying to reach these goals. So some alternative theories that have been proposed in the literature include the Horndeski or generalized Galilei lemma, as we will see, which includes an additional scalar field, for instance. And some other theories rely on exploring further properties of space-time. So instead of the metric field, we can look into torsion, to non-metricity, or to combinations of these, of the three quantities here. We can look into non-minimal couplings, and non-minimal couplings with the matter curvature or the matter Lagrangian, or the trace of the energy momentum tensor. We can look into algorithmic Palatini formulations as well. Or we can look into quantum cosmology, the forms we could spend all the afternoon talking about alternative models. But our focus here will be on the Horndeski gravity. So, did you know that Horndeski was a painter? Yes, he was. And this is a very interesting story. So in 1974, he proposed a ghost-free scalar theory up to second-order derivatives. 2 years later, he extended this model by including an abelian vector field, okay, which was invariant under U1 symmetries. Which has an interesting limit. The flat spacetime, it gives the Einstein-Maxwell action, and if you can realize some conditions, you get the Kroger action. But his works remained ignored for several years. He switched career to painter. In 2014, a different formulation of his theory has been proposed, the generalized Galilean. And later on, it was realized that, at least in 4 dimensions, both Horndeski gravity and generalized Galilean were the same. Okay? But he was unaware of his success until a PhD student came to him and asked for a painting for his thesis on his model. Okay? So, this Horndeski gravity, it contains general relativity, Brans-Dicke, and many more models, even f of r theories upon a suitable conformal transformation. So, let's recall what is a Galilean theory. A Galilean theory is a field pi which obeys this symmetry. This is a Galilean symmetry. Of course, we can covariant. We can generalize in order to have a covariant version, but when we do that, we break the Galilean symmetry. But there's an interesting thing, which is it gives rise to field equations of order none higher than 2 in the spacetime derivative, in such a way that both classical and quantum pathologies are absent. So, as I said, both Horndeski scalar gravity and the generalized Galilean gravity are equivalent to each other, at least in 4 dimensions. Okay? So, as I told you, gravitational waves put a very stringent bound on the speed of gravitational waves. But from these constraints, the Horndeski gravity repassed in the generalized Galilean version can be put in this form as a sum of these gravity Lagrangians. Okay? So, these 3 functions, because this is a constant, these 3 free functions are functions of the scalar field, and some can be both of the scalar field and of the kinetic term. So we move forward to a problem that we know that exists in gravity. So how we classify energy in gravity, for instance, in general relativity. We know that for asymptotically flat spacetimes, we can have a unique total energy momentum for vector, which is conserved. This is precisely what is used, but you know that there's some freedom even in that, so that we'll reach to the ADN mass, to the Bondius mass, or to the Lamarck's mass. Okay, so in 1979, a proof of the conjecture of this energy problem has been put forward by Schoen and Dial, but it was a lengthy proof. Okay, in fact, 2 years later, Witten reached to an elegant demonstration of this conjecture. So he studied the stability of supersymmetric solutions of supergravity theories, and he showed that the ground state of n equals to 1 supergravity and Minkowski space is stable both classical and semi-classical. Okay? We can look into the Witten's theorem in the Nestor's version, which is more interesting for technical purposes. Okay? So this is precisely how we can relate total energy momentum tensor for asymptotically flat spacetimes, which is given in terms of this connection. Okay. So this is a two-form here, a two-form, being epsilon the Dirac spinor and gammas the Dirac matrices. This can be recast in this form. Okay. Looking to this. But this is not just a normal covariant derivative. It's the supersymmetric extension based on the Gravitino, how Gravitino transforms upon supersymmetric transformations. And we get this, the Einstein tensor, we have this, and the connection here, and we have this chi field which is related to the spin 1/2 fields upon the supersymmetric transformations. Okay. In general relativity, we know that from the Einstein field equations that the Einstein tensor is equivalent to the energy momentum tensor. So, to ensure this quantity here, which is the integrand of this here, okay, so that we can ensure the positivenesses, the energy momentum tensor of matter fields needs to satisfy the dominant energy condition. This quantity here needs to be is not space-like, and that the Witten condition is chosen. Okay, this result has been generalized by Boucher in 1984 by looking into non-supersymmetric theories. Remember that by supersymmetry, these quantities here are set. Okay, but for non-supersymmetric theories, these quantities are found to be of this form. And this has been applied for some models, okay, by Bertolami and Bertolami. Okay, our results. We found that one of the three functions, which was a function of the scalar field and the kinetic term, is solely a function of the scalar field, together with a set of relations that need to be satisfied. Remember that these f functions are related precisely to these forms for non-supersymmetric theories. Okay. So, and we can also look into a boundary condition, provided we look into n equals to 1 supergravity limit. Okay. We have found that zero energy states are stable. We can also look into other stability criteria, namely the attractive gravity, which poses that the gravitational coupling needs to be positive. But this is precisely interesting because when we look into the gravitational waves constraints, we find that in order to avoid ghost grid instabilities in the speed of sound, we find that the G4 is precisely positive. Remember that decoupling in this surviving Horndeski, the surviving subset of Horndeski gravity theories is precisely 1 over G4. Okay? So these agree. And as far as the Dolgov-Kawasacki instability, which lies when the rich scalar has is dynamical in the sense that the trace of the field equations leads to a dynamical equation for the rigid scalar. But this is not the case for this variable subset of theories. Hence, this renders an algebraic equation for the scalar curvature. Hence, no Dolgov-Kawasacki instability is expected. Okay? As for the implications of these results, so as for inflation, we found that the viable models that provide inflationary solutions in the so-called slow roll regime are the ones where we have an effective potential which is roughly G2 of phi over G4. Remember that G4 was already constrained to be solely a function of phi, And this is not a constraint from the Witten positive energy theorem, but it is a way to get rid of the kinetic terms in the solar regime. Okay, so the potential term dominates over the kinetic one. So as for the cosmological constant, upon a suitable identification, again with n equals to 1 supergravity, we found that the cosmological constant arises precisely as it is constant. This quotient which needs to be constant. Okay? So we have, and again, we find solutions for these functions f. Okay? So, reaching the end of this talk, so we have discussed briefly Horndeski scalar gravity theory has an alternative gravity model. We have seen the Witten's theorem applied to this model, and we have seen also some stability criteria. In the next weeks, I hope, a following paper will appear regarding DOST. This is a exactly DOST, right? Why DOST? Exactly. It's it's a joke. This is a joke. So why we look into DOST? Because it's an extension of Horndeski gravity, although not involving those instabilities. So thank you very much for your attention.
Okay, I have a couple of questions. The first is how supra enters the game. I didn't get that because you know, in the literature you can find reconstructions of R squares supergravity or some very simple modified supergravities, but there is not a supergravitational extension for dense gravity. However, I mean, my question is, you show the stability conditions in the end, but lambda CTM, I mean GR, lambda CTM and weak denses are subclasses of dense gravity. So why, I mean, so you expect to have these stability conditions even in pure scalar field inflation models. So why, I mean, can go back one or two transparent? Yeah, there.
Okay.
So for instance, why lambda is G2 over G4? Because simple lambda is also a part of potential. I mean, in Horndeski actually you have the scalar field potential in the end. And you can add the cosmological constant.
Okay. You see, okay, I see your point. In fact, we can, by choosing the function, the free functions, we can include a cosmological constant. Right, yes. But this is ad hoc. You do not find any fundamental motivation for that, right? It's like driving Einstein field equations, it's an integration constant, roughly, right? So this intends to, given the motivations of n equals to 1 supergravity, to find a reason, some reason by appearing a cosmological constant, in this sense, okay? By inspecting the n equals to 1 supergravity. But yes, you could add an additional cosmological constant. And even you can have like the total cosmological constant, right?
Any other questions? Yeah.
Can you tell the joke?
Sorry?
Can you tell the joke?
The joke. Oh, okay. So this is DOSTE. DOSTE, if my communication is okay, DOSTE means why. So, and DOSTE is similar to DOST. DOSTE means why, and DOST is degenerate Horndeski scalar theory, right? Okay, so
Whose joke is this? Is this Shinji Tsuchikawa? Who's responsible for this joke, right?
I was.
Oh, you are.
I remember when preparing this presentation that DOST resembled another word. What was that? It was why in Japanese. So it's just merely a joke to.
What do your Japanese colleagues think of it?
Oh, I don't know.
I'm gonna ask them.
Okay, of course.
Yeah,
lot. We'll thank Cláudio.